Okay, so you guys get a chance to look at the learning target, or you want me to leave it up a little longer? Yeah? Cool. Okay, so we're gonna start by watching a video.
Oh, here, just hit it over here. Oh, then go back again. I don't know, it didn't. It's a dumb board.
That's okay.
Okay, now put the link. There we go. Let's see if my speaker.
Gettable vacation memory. It didn't actually begin here. This memory began when Dad...
Let's talk about waves. No, not like that, but waves like this, or this, or even this. Welcome to Movie, Math, and Science and Waves. A wave is a repeating movement or disturbance that transfers energy through matter or space. Waves transport energy without transporting matter from place to place. Waves are produced by vibrations. When this net hits the water, it causes vibrations that produce waves. The medium is the matter through which waves travel. The medium can be a solid, liquid, gas, or a combination. However, not all waves need a medium. Light and radio waves can travel through space. Mechanical waves can only travel through a medium. In this video, I'll discuss two types, transverse and longitudinal, also called compression waves. With transverse waves, the particles in the medium move back and forth at right angles to the direction of the wave. And here's the anatomy of a transverse wave. Longitudinal waves, also called compressional waves, have the particles of the medium move in the same direction as the wave. They also have dense regions where coils are close together called compressions, and less dense areas called rarefactions. The wavelength of a wave, which is represented by the symbol lambda, is the distance from crest to crest or trough to trough in transverse waves, and from compression to compression or rarefaction to rarefaction in longitudinal waves. The frequency of the wave is the number of wavelengths that pass a fixed point each second, and they're measured in hertz. Here's high frequency and low frequency. If you'd like to know more about waves, this playlist will help. And as always, thanks for watching, and Moo Math uploads a new math and science video every day. Please subscribe and share.
Grammarly is a digital writing assistant that helps more than 20 million people write.
Yeah. Okay.
See. Okay, and then go ahead and jump into the bell word. There's just a short little thing for you to answer, and there's a word bank. So I'll give you a few minutes to do that. How are we doing on time? Everybody okay?
You need more time, or are you good? Thumbs up?
You good? Awesome, cool. So for the next part, we're actually gonna go into groups. So we can do 3 and 2 or 2 and 3. So what we're gonna do is we're gonna get like really big slinkies and we're gonna go out in the hallway in our groups and we're gonna demonstrate the difference between transverse and longitudinal waves with our partner. So go ahead and get into your groups and I'll hand out some slinkies for us. So,
You want groups of 2?
groups of 2 would be good.
So do you want to go to a lab table with their partner? or
Yeah,
you
go
want
ahead
to-
and go to a table and I'll hand out the slinkies.
Did you take your testing? Okay, so the dates to look up are June 1st and 2nd. So it'll be June 1st at 3 p.m. and June 2nd at 8:30.
And
Yeah. Okay. I'm gonna send out a Google invite. You're gonna use it. It's like a Google class. No, you can do it online. Who do you want to work with? You want to work with Devin? You want to work with Brendan? Well, it's just you're going to be on one end of a slinky. You'll be at least 12 feet away from me.
yeah. Or you can be stuck with me. We can.
Let's start with the basics. First of all, we are showing different kinds of waves, and the 2 kinds of waves are transverse waves and longitudinal waves. A transverse wave, you want to think it starts with a T, so it goes down, it's a T, you have the motion or the energy goes that direction, but the vibrations are perpendicular to that direction of motion. Just like when you traverse, or you go across a canyon, or you traverse a bridge. The other one, the longitudinal wave, is also known as a compression wave. Okay, so compression wave goes parallel to the motion, transverse wave goes perpendicular to the motion. Now, other things that we can do, let's talk about the speed of the wave. Just as in other kinds of harmonic motion, the amplitude does not affect the speed. I'm going to do a small pulse and a big pulse. Small pulse, big pulse. Now, let me do them on top of one behind the other, and we'll see if they catch up with each other. Notice even when they reflect, they stay away from each other. We'll do it one more time. So you'll notice, if you look carefully, that the large wave did not catch the smaller wave. I think most people would think that a bigger amplitude, the larger wave, would move faster, but it never catches it. The only thing that a large amplitude does is it has more energy, so it'll go farther before it dampens or dies out. Well, this is no different than a loud sound being heard from farther away than a weak sound. It has more amplitude, so it can go farther before it dampens. All right, now let's talk about constructive and destructive interference. We have someone at the other side that's going to help me out here. Both of us are going to go this direction, and we have these squares here that help us out. We're going to go to that spot. Oh, before I do that, sorry. Speed of the wave. I can actually make it faster by pulling in the coils. That makes it tighter, and watch how much faster the wave is. You should be able to see that that's significantly faster. And notice it goes farther too. It goes back and forth more often, or more times. And the reason for that simply is that there are less coils touching the ground, so there's less friction. Okay, sorry about that. Oh, another thing I didn't show, I apologize, this is not perfectly scripted. I'm going to have you go ahead and do a transverse wave, and I'm going to do a longitudinal wave at the same time. Ready, go? Make yours a good snap. Ready, go. Now, the kids are usually pretty surprised by that. We get a lot of ooh, ah, but 2 people can talk in a crowded room at the same time, and all of those waves go through the same air. Okay? Now, I'm going to do a snap. That goes 1 square. You do a snap, 1 square. There we go. Watch in the middle when they cross. 1, 2, 3. And you will notice, let's do it again. 1, 2, 3. And you will notice that the combined wave, these are vectors, these are scalars, they just add together, and we got 2 squares instead of 1 square. But what if I go the opposite direction? I'm going to do this, and he's going to do, all right, watch what happens in the very center. Let's wait till it happens. Ready? 1, 2, 3. Okay, we'll do it again. It's a little hard to see, but you should see right there in the center that instead of it making a big wave one over the other, it actually just rotates or pivots. 1, 2, 3. Because that would be destructive interference. If we want to call this a negative amplitude and a positive amplitude equaling 0. The last thing I want to show you here with the slinky is, first of all, his hand is fixed. So watch what happens. We can show his hand down there so we see that it's fixed. All right, and watch down on that end what happens to the wave as it passes. It inverts. It goes to the opposite side of the slinky. Now, he's going to use a string instead. Okay, put the string down, pull down a little farther away. All right, now watch what happens. This is known as an unfixed boundary. The other was a fixed boundary. Okay, pull your hand up just a little bit off the ground. There you go. Notice the pulse stays on the same side of the slinky. So if there's a fixed boundary, fixed, hold, fixed boundary, hold on to it. There we go, fixed boundary, inversion, unfixed boundary, no inversion. And in my class, just for fun, we call that inverting and verting. I know it's not a word, but it works out. All right, there's a slinky lab.